We're going to show you some computer visualizations of results from climate change. So first we're going to talk about the history of the buildup of greenhouse gases, particularly carbon dioxide. We know this from direct measurements in the last 60 years, but before that, inference from carbon dioxide detected in bubbles trapped in ice cores taken from Greenland and Antarctica and mountain glaciers. Here we have the carbon dioxide level. It varies seasonally from 1979, when it was 335 parts per million, which is 0.0335%, and it continued to go up then to the current value of slightly above 400 parts per million, or 0.04% of the atmosphere. Here we have the curve, the so-called Keeling Curve, which has all the carbon dioxide measurements going back to the first ones in 1957. And we see there's been a continual increase such that carbon dioxide in the atmosphere is now about 40% above its value in pre-industrial times, which we also know from the ice core measurements, when it was about 280 parts per million. What's contributing to this warming? As you all know, it's a result of the buildup of the greenhouse gases produced largely by combustion to produce electricity, to provide transport, such as burning gasoline and diesel, and about 25% of it results one way or the other from agriculture, from various emissions, including the fossil fuels that go into cultivation. Here we have night lights from both urban areas and from some kinds of combustion, namely fires from flaring at oil and gas operations, when methane is burnt off at the top of the oil wells. And we also have, these are fires from settlements, but we also have fires from burning in the tropical regions, particularly across parts of Africa and intensely in the Amazon. This is a single of one of the main sources of greenhouse gases, aside from combustion to produce energy, namely the cutting and burning of forests to clear it for agriculture, after taking out the timber, and eventually for animal grazing. We should always keep in mind that, therefore, there are two large parts to this problem. Development for industry, with the direct combustion of coal, oil, and natural gas, and the results of deforestation.
These are observations from the Amazon rainforest. What you see here is one of the world's largest carbon sinks. In fact, we know that forest systems in the world absorb 25% of our emission of greenhouse gases, 10 billion tons of carbon dioxide each year. But to keep the Amazon rainforest stable, to be able to perform this enormous subsidy to the world economy, we need to have exactly what this map shows here, very intact forest systems. But as we see here, the evolution over time, where you see the infrastructure and road access and deforestation increasing. And what happens is that despite the fact that you have patches of forest intact, they become so small so they cannot keep up their self-moisturing ability to generate rainfall and keep the ecosystems intact. So while you're breaking up the systems, you end up in a situation where science now indicates that we may actually be facing the risk of tipping points where rainforest could irreversibly shift over to savannas, which would not only be an enormous burst and loss of carbon dioxide, but it would also affect rainfall patterns across the world with ramifications on food production. So we depend on forest systems also for the climate stability.
But that initial road built into the Amazon, while there was nothing going on in this particular area, was a matter of government policy. But once the road's built and a decision by the government to encourage people to come in here, you see that tremendous fragmentation occurring as people use the road, then build other roads and settle and clear. This shows the deviation of Earth's temperature, and you can see the red indicates a gradual warming, which is basically encompassing the whole map. The last 3 years, we found out in the last couple of days, were the hottest on record, with the temperature now about 1 degree Celsius above this long-term average. And this is the first time in the history of the record that 3 years in a row were successfully each hotter than the previous one.
Now, we also have increasing evidence, when you look back from ice core data, that since we last were in an ice age 12,000 years back, we entered the Holocene, which is this extraordinarily stable interglacial phase when we invented agriculture, we developed modern civilizations, and we have evidence that the the variability during these 12,000 years of average global temperature is between plus minus 1 degree Celsius. So 2016 might be the point where we now have evidence that we've hit the ceiling of a maximum temperature since the last ice age. So this is a very decisive point in terms of support for the need for decarbonization into the future. What you also see here is from 2016, if we would have gone to 2015, you would have seen increasing red right at this Pacific Ocean part here, which is the source of energy in the oceans. 95% of the heat caused by our emission of greenhouse gases and the greenhouse effect when the atmosphere absorbs heat radiation from planet Earth is absorbed in the oceans. So 95% of the heat is, so to say, shoved under the carpet and hid deep down in the oceans. This is what is upwelling and accelerating ice melt, but this is also what causes the unprecedented El Nino effects, where the last time we had an unprecedented El Nino was 1998. It was an outlier in terms of air temperature, but it also caused dramatic bleaching of coral reefs in the Pacific Ocean and the Indian Ocean. And now we'll see what happened in 2015, which was an even worse El Nino event. And we see here the coral reef bleaching and temperature anomalies for 2015. And these are very dramatic illustrations of what is happening over time. You see 2013 coming into 2014 before the El Nino event. It's building up, and then comes gradually a heat point which will be accentuating in the 2015 part, where we really deviate to a point where we start seeing the dramatic bleaching, dying out of the symbiotic relationship between bacteria and the hard coral reefs. Here we have it. There you have the large Pacific and Indian Ocean coral bleaching events, which are so dramatic at this point that for the first time we see bleaching occurring to a large extent even in the Australian Barrier Reef, which was so resilient and capable of withstanding the 1998 El Nino, but was not able to withstand the 2015-2016 El Nino event. And this is particularly important to recognize, because the reason why coral reefs are so hardly hit now is not only because of the temperature rise causing bleaching, it's also because of the acidification of the oceans. 25% of our emission of greenhouse gases are taken up in the oceans, another 10 gigatons, 10 on land, 10 in the oceans, half of our emissions. And then you have eutrophication and overfishing, which means that the coral reefs become weaker to deal with these kind of shocks and stresses. So here we have evidence of a multiple stressor pressure on systems which, to supply the livelihoods for many 100 million people living in coastal regions. So this is a dramatic and very significant undermining of economic development for many communities around the world. For a coral reef to rejuvenate after a dramatic bleaching event, they need fish, and they particularly need grazing fish like parrotfish that during that sensitive collapse phase can keep all the algae away by grazing on top of this destructed coral reef, so the coral reefs get a chance to grow back. But because of overfishing, we see many, many examples, like in the Caribbean, like in the Indian Ocean, where there's so little fish that when the coral reef collapses, algae just takes over and you come into this soft algae, eutrophied, unhealthy state that does not deliver to the economy. So we need to understand that climate change impacts on coral reefs depend also on maintaining biodiversity in the marine systems. In the oceans, climate change impacts oceans by heating, by acidifying, but biodiversity plays a role to keep the system strong. Same on land. To keep our agricultural systems operating, to keep our landscapes operating, to keep our water supply operating, it's not only that we need to have forests and we need to have average temperatures low enough. No, we need to have biodiversity and ecosystems that have the ability for pollinators and predators and systems, animals and plants, to keep the systems functioning. This map shows the first evidence globally of the sensitivity to climate change in different ecosystems. And the red parts are the most sensitive already at our current warming, while systems in green are more able to deal with climatic shocks. And again, this is the message that when we are dealing with, trying to adapt to climate change, we must also invest in strong biodiversity and ecosystems.
The other extremely sensitive system is the sea ice in the Arctic. Sea ice has shown a linear decline since satellite measurements observations began in 1979, and here we're rolling forward the sea ice extent. You see both the seasonal growth and then diminishment toward September, which is the minimum month of extent. And you can see on top of that seasonal oscillation, there's a clear downward trend in the extent of ice, so that by now there's only about half as much summer sea ice at the end in September as there was at the beginning of the record in 1979. And the projections are, if this warming continues and even accelerates perhaps, that the extent of the summer sea ice by mid-century is going to be zero, basically. The Arctic, like the coral reefs, are not just a natural system. They're what we call a social ecological system, because humans depend on the particular shape of the ecosystem in both cases. And we're just going to do this earth-shaking transformation in the north, and it's already well underway.
The Arctic, as Antarctica, are systems that regulate the stability of the entire Earth system through the albedo and the cooling of the planet. So the drama in the Arctic does not stay in the Arctic. It affects potentially the stability of the whole planet.
Correct, through the positive feedback of open water absorbing more heat because ice reflects sunlight. And mountain glaciers like the Mendenhall Glacier in Alaska, which you can see retreating here, have been retreating virtually worldwide. There are some that are growing at the very highest elevations in the Himalayas and a few other places. But basically, there's a general retreat of mountain glaciers. They will more or less be gone over the next century or two if the high emissions scenarios come to pass. And they are adding to the height of the sea level. The Antarctic ice sheet contains an equivalent of 57 meters of sea level rise. Most of that would only melt if warming got into the double-digit Celsius range. So this is a feature called an ice shelf. Here's the edge of the continent. This ice is floating. It's the extended floating tongue of these land-based glaciers. Here are the mountain ridges. Here's the ice in between. The glaciers merge into the ice shelf. The ice shelf eventually produces these icebergs as it travels into the warmer ocean. But look here. You see these dark spots? These are melt ponds on the surface of the ice shelf because in summer it gets warm enough for water to form in Antarctica. Underneath, the ocean waters are also over some periods have warmed, so you get melting at the top of the ice shelf and at the bottom. Now, this series of events occurred over just 6 weeks in 2002 when the warming just got too much for this part of the Larsen B ice shelf. Slowly, it starts to fragment, and then it becomes, this is open water. It's like slush. It's just open water with icebergs in it. So we went from a fully integrated ice shelf with just a little hint of warming on top from those melt ponds to basically open ocean with some icebergs drifting around. And that, again, occurred over a period of only 6 weeks. The size of this, I think, is about 50 or 70 kilometers on a side. That's what the dimension of that feature is. And as soon as that happened, these mountain glaciers accelerated and started running at up to 8 times their former speed into the ocean, creating sea level rise. Luckily for us, for the time being, this part of Antarctica, the Antarctic Peninsula here, is very skinny, and it doesn't have much ice on it. So even if this process just went on unabated here, it would only add a few inches or 5 or 10 centimeters to sea level rise. But over here, in other parts of Antarctica, particularly over this way in West Antarctica, you have much bigger ice shelves that, because they get stuck on the ocean bottom as they begin to travel forward, they're penning back a very large amount of ice, and that's where that 3, 5, perhaps as much as 10 meters, if you include parts of East Antarctica, of potential sea level rise could come from.
So we clearly have unequivocal evidence of the impacts of climate change across the world. We have unequivocal evidence that it's human-induced climate change the primary cause. We're starting to see invoices in terms of droughts, floods, heat waves, and impacts from climate change on societies. But a question that is increasingly rising is also, are we seeing geopolitical complex interactions between abrupt climate change and collapse of societies? Well, you've all followed and follow worryingly the civil war in Syria, the dramatic humanitarian crisis and the geopolitical collapse in Syria. And today it is important, and many scholars are increasingly digging into the evidence that we can no longer decouple climate change from what's happening in Syria. And the reason for this is that 2008, 2009, 2010, and we're seeing some evidence here of how irrigation systems and farming systems were basically shut down during the years just prior to the civil war, because we know from observations that these 3 years were the worst observed droughts in Syria probably over the last 8,000 years. And I mention 8,000 because this happens to be a very critical region in the world, because this is where we invented agriculture, in the Mesopotamian, Tigris and Euphrates region 8,000 years ago. So this might be the unprecedented worst drought condition ever on record. 2 million farmers left the rural areas and flooded into cities like Homs and Aleppo, causing even President Assad to issue warnings of worry prior to the civil war of what kind of destabilization could this cause, that we're suddenly having an instability in food supply driven by these unprecedented droughts that, of course, droughts like El Nino are natural events, but they seem to be accentuated by human-induced climate change. And that's where we then see the implications geopolitically with the Syrian civil war, which clearly we cannot say climate change caused it, but equally clearly we cannot decouple and say that climate change had no influence. It seems to be the first example of a social, ecological, complex interaction leading to collapse. And then we see the dramatic data here for the first time mapped in this way of the 2012 refugee fluxes exploding out of Syria, moving in all directions. You see Turkey being one of the big recipients, and then there is a trickle, but we all know what enormous political implications that trickle has had on the European Union over the last few years, with Syrian refugees flooding into the European Union as a result of this civil war, which for the first time we start seeing indicative evidence that we cannot decouple it from climate change, social, economic, and political disruptions.
We're going to look at sea level rise projections. This data is from Climate Central, and it looks at a fairly bad scenario of if we don't fight hard enough to reduce reductions and we end up greenhouse gas and we end up with 4 degrees sea rise. This is the long-term sea level rise coming from that 4 degrees rise. First, let's look at the coast of China.
At 4 degrees, just to remind us, is the business as usual path we're following today. If we do nothing, we on average, according to IPCC, are projected to reach 4 degrees by the end of this century.
So moving over to the U.S. here, this is what Florida looks like today, and this is the eventual loss at a 4-degree warming. We don't know exactly whether that would take centuries or perhaps even into the millennial time scale, but it's obviously you lose half the state of Florida, you completely lose southern Louisiana, New Orleans is long, long gone. But even if, let's stop it at 2-meter sea level rise, you notice, again, New Orleans is gone even then, and in Florida, the Miami area is gone. And this area cannot be protected. You can't build a seawall like that, and even if you had the money, this limestone base is porous, water gets under the seawall eventually and comes up. And the thing to remember is the last time Earth was 2 degrees warmer during a period called the last interglacial 125,000 years ago, global sea level was somewhere between 6 and 9.5 meters higher than today. We don't know whether it took 1,000 years to get there or it took 100 to 200 years. But that's the direction we're headed if we let it warm 2 degrees or more and then don't let it cool after that.
We may be facing exactly what you're seeing on the screen here, dramatic, devastating sea level rise implications that could reach 2 meters this century, affecting hundreds of millions of people and also property worth billions. So this is not science fiction. This is something that we may almost be committed to. Science indicates that we may much, much earlier come to the point where we irreversibly commit ourselves to this. So the Greenland ice sheet holding 7-meter sea level rise will not melt over decades. It will melt over centuries. But the point at which we cross a tipping point where we irreversibly commit ourselves to the melting, where we have no way of turning back, may come already over the next decades. It may already occur between the 2 to 3 degrees Celsius warming level. So that's something to recognize, that we need to now act proactively to avoid irreversible change.
Bangladesh is often held out as the most vulnerable spot to sea level rise, where a lot of people live, 160 million people in a very small area. And you can see as we move forward through the 4-degree estimate, you dissolve about a third of the country right up to the capital of Dhaka, which is where the rivers join, or near where that merge in the rivers are. And the southern part of the country, where only is vulnerable to even a meter of sea level rise, and about 10 million people live in that area right now, a little more.
And we live in a world where we have a whole handful of low-lying island states that, as you know, are currently, even already today, negotiating evacuation plans to be able to deal already with a 1 meter sea level rise, which today is almost the most conservative estimate for this century. Already at that point, you have nation states potentially disappearing, like the Maldives, like Tuvalu. And this is something which is, and it's important to recognize, it's not only that the sea rises and suddenly you're drowning. No, it is that even just a half-meter sea level rise leads to much, much more dramatic floods, much, much more salt intrusion, much, much more erosion. So you'll have to basically leave the livelihood points in coastal regions way before you're, so to say, underwater level, given the dynamics of the more powerful water pressures that occur. To keep the big biomes on Earth as carbon sinks, we depend on functioning oceans, we depend on functioning rainforests to be able to stay in an interglacial state that can support the world economy. And as we approach 2 degrees Celsius, science starts indicating that we might lose these carbon sinks and move towards the most dramatic situation of all, when Earth goes from being our best friend to being a foe which self-reinforces warming at a pace that we can no longer control. And that's why the Paris Agreement is so important. We know we have to bend the curve of global emissions no later than 2020. In 3 years' time, we need to start really moving towards a decarbonization of the world economy. Why is this important? Well, it's because carbon dioxide is a long-lived gas in the atmosphere. It stays for 1,000 years. So the more we delay, the more we just put the debt and the invoices to future generations. And then we need to follow a pathway that leads to a net zero, a fossil fuel-free world economy by mid-century, in 33 years. This is a revolution. If everyone follows a carbon law of halving emissions every decade, we actually stand a chance to aggregate at the global level at a safe pace that would take us away from these worst-case scenarios.